Hello and welcome to the second video of STM's new short clip video series. My name is Ole Carstensen, and in this week's video I will explain and showcase some of our atomistic polymer modeling capabilities. But before we jump in, let me point to the video description, because there you can not only find all the input files for the simulations, but also useful information regarding a free trial of our software and some more information on this video series. In this video, I will use the reactive force field ReaxFF, which is part of the Amsterdam modeling suite, to demonstrate how one can generate realistic thermoset polymer structures. And once I have obtained such structures, I can then use them to predict the material's mechanical properties from an MD simulation. One of the archetypical thermosets, I shall use an epoxy resin, and the epoxy is hardened with an amine curing agent. The basic reaction that happens during this curing of the polymer is shown here. During the curing, many such crosslinks will be generated and a more or less rigid 3D network is formed that will give the material its unique properties. Of course, different epoxy hardener combinations will result in different 3D networks. This is reflected by a varying number of crosslinks on the atomistic scale. To quantify this number of crosslinks, I shall introduce the crosslinking ratio, which is defined as the ratio of the crosslinks that could in principle be formed versus the number of crosslinks that are actually formed. It's important to note that the crosslinking ratios of today's epoxy materials are quite high, with typical values of around 80–90%, but not perfect. So the longer this curing goes on, the more reactants will get immobilized or shielded off from others inside the forming network. And I'm saying this because these small imperfections in the network are crucial features of the material. If we don't get those right, our simulated properties will be flawed. Now, let's see what happens when we just run a simple molecular dynamics simulation with standard settings and an epoxy and a hardener molecule. Just throw them in a simulation box and then we calculate the dynamics of the two. And I have already prepared this. This is what it looks like. So you can see the two molecules moving, time passing, but what you do not see is a reaction. So there is no reaction yet, but I can already tell you there also will not be any reaction anytime soon. And the reason for this is that in the lab, this curing reaction takes place on a time scale of hours. That's an eternity in terms of atomistic simulations, where we can afford the simulation of, say, a couple of picoseconds or nanoseconds at best. So what we'll have to do is we'll have to resort to some sort of acceleration technique that allows us to speed up the reaction, but also accounts for unsuccessful reactions, because we do want a realistic, slightly imperfect structure at the end. The acceleration method that can provide that and that we shall be using is called the bond boost method. Here's how it works. Okay, let's take another look at the curing reaction. Before it can take place, the reactants need to approach each other in a certain favorable manner to form some sort of loosely defined preliminary complex. The reactive centers are then roughly in the correct orientation towards each other, and once we detect this configuration, we now switch on an external restraint energy as follows. Here F1 and F2 are user-defined force parameters, while Rij is the current distance between the atom pair, and R12 is the desired distance between the atom pair. So this external energy does not enforce a reaction. Instead, it supports the formation of the desired bonds. Hence the name bond boost. This is in line with our earlier requirement that the bond formation should occasionally be allowed to fail. A schematic of our bond boost simulation can be described as follows. While we run our molecular dynamics simulation, we continuously check against a set of predefined atom distances if our preliminary complex has formed somewhere in our simulation box. If it did, we switch on the bond boost, but only for the atoms part of that very complex, and only for a certain amount of time steps. During the boost period, the reaction is likely to happen, but it doesn't need to. So that's the trick. Here's what a bond boost simulation looks like when it's set up in ADF input. Okay, so here's what the bond boost input file available in the video description looks like in ADF input. Now I won't go through every step of the setup because you can find a step-by-step tutorial for exactly this system on the SCM website. The link to that tutorial is also in the video description. The bond boost settings are found in a separate panel under Model, Bond Boost, and they consist of two parts. The first upper part identifies our preliminary complex. For example, the first requirement is that the nitrogen atom and the terminal carbon atom of the epoxy group are within a distance of 3 to 7 angstrom to each other. The naming of the atoms you can see here are beforehand provided by the user. So this is done in the regions menu. If I go to Model Regions, I will get into the regions menu. And here you can add, remove, or edit the atoms that will define your preliminary complex. So if I just select CT and all N for all nitrogens, you can see them displayed here. Now back to the bond boost menu. We take a look at the second part, and the second part defines the actual bond boost. That is the external energy that will be applied once the above complex was identified. If you just look at the first line, you will see that we want to support the formation of a carbon-nitrogen single bond with a bond length of 1.5 angstrom. On the top, we request the bond boost to be active for a duration of 10,000 iterations. So that is the time period during which the reaction may or may not occur, and after that the boost will be switched off. Now in the ReaxFF main panel we have set our parameters for a fairly standard NVT molecular dynamics simulation at a temperature of 500 K, and we choose a dispersion corrected force field. That's the same as in the online tutorial, but there are other options available too, including a dedicated bond boost force field. So let's see what happens when we now save and run the calculation. We can go to File, Save. I saved that before. And then File, Run. Okay, so once the simulation has started, we can follow the progress in ADF Movie. So I select the calculation, I go to SCM Movie. And here I can see a movie of the trajectory. we can already see the reaction happening. Oh no, it has already happened. And a good first indicator if you want to check for reactions is usually the number of molecules available from the properties menu, number of molecules. So just select that. And there we can see that the number of molecules has reduced from 2 to 1. If we want to build a realistic model of a polymer, we are going to need more monomers. So let's go back to the input and see how we can increase the number of molecules in the simulation. First, we switch on the view of the lattice vectors. So you go to View, Periodic, Show Lattice Vectors. So now we can see the size of our simulation box. We can proceed to the Builder tool found under Edit, Builder, and simply add some more molecules to our simulation box. I have provided a single BiSF and DATDA molecule for download in the video description. So after you download them, you can import them directly into the builder by clicking on these folder icons. So I select the BiSF epoxy molecule and a hardener molecule. For now, we shall be adding 7 epoxies. So I changed the 100 to 7 and 3 hardener molecules, totaling to 12 molecules because there are already one of each kind in the box, with an epoxy hardener ratio of 2 to 1. Now note how the density below here is updated even though we haven't actually added any molecules yet. I'm going to try and obtain a density of around 0.3, 0.4, and I'm doing this by adjusting the lattice vectors shown on the top. So I'm doing a 30 angstrom, maybe 25. Yeah, that looks good. So a lattice vector length of 25. If the density becomes too high, the program won't be able to pack the box without collisions. If it's too low, equilibrating a final density will take a long time. So once we have done all these, we just need to click Generate Molecules. And can close the builder. Now we're almost done. All that is left is the labeling of reactive centers. If you look closely, let's zoom in a bit, you can see that the reactive centers of the newly added molecules are not labeled yet as indicated by the glowing spheres. To add the labeling to the new molecules, go to the Regions menu, found under Model, Regions. And from the arrow drop-down menu to the right of each entry, so that's a region entry here, and that is the arrow drop-down menu, select Apply to Identical Molecules. And do that for each of the region entries. You can double check by checking the checkbox on the left side to the region entry if all have been successfully applied. Now, in a final step, let's map the structure back to the simulation box. That you can do by going to Edit, Crystal, Map Atoms to 0, 1. And there you go. And now we are ready to run the simulation. Let's just request a few more steps this time. Say twice as much, 80,000. so we can see some more reactions occurring. Now just save and run the calculation the same way as we did before. And again, the process can be monitored in the movie program. This time the simulation box is a bit bigger, so the calculation will go a bit slower. Now, after 80,000 steps, we see that quite some reactions have occurred in the system, which reflects, of course, in the number of molecules going down. But let's switch to the periodic view real quick. Go to View, Periodic, Repeat Unit Cells to get a bit of a better picture of what our formed polymer looks like. This is, of course, not finished. But not every reaction will result in a lower number of molecules. So let's calculate a proper cross-linking ratio. For this, we will use a small Python script that is again linked in the video description. Just download it and place it in the folder where you ran this bond boost calculation. Then open a terminal window from ADF Movie. The terminal window is available from the Help menu. And type sh to enter a minimal-like Linux shell environment. Now you can run the script via the AMP's Python interpreter, and you just need to pass the name of the trajectory as an argument to the script. Now the AMP's Python interpreter is called start Python, so we type start Python. You can use tab completion, and the name of the script that you downloaded is cross-linked density.py. Again, tab completion comes in handy. And finally, the name of the trajectory, which in my case was called simple bond boost calculation. I'm using tab completion again, .rxkf, and hit enter. Once done, the script will print the final cross-linking ratio as well as the history of the cross-linking ratio throughout the trajectory. The final cross-linking ratio is written to the command line, so we can see here that's .66. It's already fairly high. And the history of the cross-linking ratio is found in a file called crosslinked density.csv. So that's comma-separated values in there. And we can use our little command line utility called ADF graphs to inspect the contents of this file. So I type in ADF graphs.exe, one white space, and then the output file called crosslinked density.csv, and I hit enter. And now I can inspect the evolution of the cross-linking ratio throughout the trajectory. Now the units are not picked up in this little utility here, but the x-axis is the time, simulated time in picoseconds, and the y-axis is the cross-linking ratio. This is also explained in the Python script, and it's also in the command line of the actual comma-separated value file itself. Even though we managed to achieve a cross-linking ratio of 0.66 already, we have not yet created a realistic polymer structure. The cross-linking ratio is not yet high enough, and most of all, the density of our system is still much too low. To equilibrate the density of the system, several strategies can be used. For example, simulated annealing has been applied very successfully by the group of Adrie van Duin to equilibrate the density of bond boost generated polymers. Another approach would be a Python workflow that is part of our bond boost tutorial linked in the video description. Here's a video of this equilibration workflow. The workflow consists of a series of bond boost simulations. After a bond boost simulation has finished, the resulting structure is slowly compressed by a predefined factor. After a geometry optimization to relax the stressed system, another bond boost simulation is run. The cycle is then continued until a target experimental density is reached. Once the cross-linking ratio and density have equilibrated, one can use the structures for a variety of simulations, including glass transition temperatures, or perhaps most common mechanical properties. The mechanical properties, for instance, can be extracted from a stress-strain curve that can easily be calculated at the atomistic level. If you're interested in such a simulation, make sure to check our detailed tutorial on simulating mechanical properties of epoxy polymers. It marks a logical follow-up to the generation of a realistic polymer structure. With this small outlook, I would like to conclude my demonstration, and I'm happy to answer your questions, be it in the live chat or later in the YouTube comments. Make sure to check the video description for all the material and resources I have shown in this video.